Science, Mr. Robertson, now back in action. And today, the most boring part of the atom, the neutrons. And they're boring because the other two actually do something. You know, I have those protons. And those protons are the thing that's most important. More than anything else. Because the protons tell me which element it is. If I have one proton, it is hydrogen. If I have two, it is helium. If I have three, it is lithium. It does not matter if I go all the way down here. You know, if it has 22 protons, it is always titanium. That's what the neutrons do. It tells me what it is. It's most important. The electrons are next important. Because the electrons we've been talking about so much recently. Because we need that full outer shell. Having that full outer shell makes my atom really happy. And that's incredibly important. It controls, therefore, all of the reactions that the atom has. Everything is defined by the electrons that it has. That decides which atoms bond with which, how many atoms you need. That controls it. The neutrons. Well, they're mainly there to keep the protons apart. Now, I've told you that the protons are positively charged and the electrons are negatively charged. And the neutrons, they just are. But it's important because, let me find a toy over here, or two. If I have a plus, and I get them together, they don't want to go. They just don't want to go. I mean, I can. It's not hard. But there's a force acting against them. I'll put them on the table and then you'll listen to the sound. They just won't stay together at all. The plus and the plus, they repel. They want to move apart. My neutron comes in. You stay right here, guys. You're not going anywhere. The neutrons are needed because the protons will want to split the atom apart. And the bigger the atom, you know, if I go to uranium as 92, it has over 100 neutrons. Because it's got to have more. Hey, no one starts a fight here. It's got to have more police there for a bigger fight. So there's way more neutrons than those bigger atoms. Because what happens if this does not work? You are going to get an example of radioactivity when the atom breaks apart. Now that can happen if there's too little neutrons. It can also happen if there's too many. In fact, in a nuclear power plant, how we actually control the reactions to get them started is I take neutrons and I go and I fire the neutrons into these really big atoms. And that makes them go, oh, there's an extra neutron, I can't hold it. And it breaks apart. So too many can also be a problem. Too few can also be a problem. Radioactivity. Now, atom breaks apart. And we go, oh, radioactivity. Oh God, it's so bad. What am I going to do? 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 It happens everywhere. It happens all the time. And yes, if we have nuclear power, we concentrate in that one place. So there's loads of power. But it happens all the time. There's rocks everywhere that have radioactivity. It's out there. The sun makes radioactivity that comes to us. It's a part of our everyday life. Atoms breaking apart exists. Why we do get scared is that when atoms break apart, it follows a famous equation, E equals mc squared. Einstein's equation. Now you don't need to know this now. What you do need to know is that the E is energy, the M is mass, and C is the speed of light. Now light is the fastest thing we know. That is one big number, meaning a very small amount of mass breaking an atom can let out a really big amount of energy. And that's why it's so scary. That's why nuclear power can be so dangerous, because it's small mass, high energy. It's also why it can be so good as well. That's a bit of a side. That's a bit of a radioactivity. Got into away from it a second. Why I care about neutrons is that neutrons can make things that are different, which I haven't really spoken about. And they are called isotopes. Now, isotopes are things where I have the same number of protons, but I have a different number of neutrons. Let's be really simple. I can have hydrogen. Now hydrogen, if you go on the periodic table, at least the one you have, we'll say this, 1 and 1. So it has 1 proton, 1 electron, and 0 neutrons. Plus, minus. I can have an isotope of hydrogen, which actually is 2, 1. Meaning it would have 1p, 1e, and 1 neutron. This is called deuterium. It looks like so. I can also have one which is 3, 1, which will have 2 neutrons. They are all hydrogen, 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 hydrogen. Really hard word to say, hydrogen. There, much easier. But they have a different number of neutrons. It gives them slightly different properties. We use this actually in space science because we can make water with this, of course water being H2O, och then vatten väger lite mer. So we can use it for reactions to measure things from space that are really, really tiny, because it's a little heavier and it slows them down a little bit better. But it's the same. This is still water. It doesn't change the actual reactions. It doesn't change how the atom works. The neutron just stays there. What we do use this for, really interesting, 2 other things. One is dating. Because some of these isotopes are radioactive. But they can last for millions and millions of years. A good example is what is called 14C. It's carbon, they're cool, but it has 14 as a mass number. Normally it has 12, so it has 2 extra neutrons. It makes it radioactive, but it lasts for a very, very long time. And it's carbon, det är vanlig carbon. Så det finns I träd, det finns I grejer som vi har använt. There are no wooden axes and stones we find, maybe in Viking farms and so forth. So what we can do that to see how much 14C there is left, and with some maths here to see how much percentage is left, work out how old it is about. That's a really cool use of isotopes. We've got a radioactive one here, and we can look and see how much is left and then go, aha, That's a great example there. Something could be this old, 20,000 years old for an old bit of tree or something like that. We could also take this bit off here, use it for health. Now, there's two ways of doing this. One is, well, they're both using radioactive isotopes. One way is to make a material, a protein, with radioactive isotopes, which only goes to cancer cells. The cells which are going out of control in the body. Now if you do this, you take the protein to the cancer cells, then only the cancer cells get the radioactivity. So you target just those cells and only those cells die. Another way of doing it is to use something called a tracer molecule, which goes to a part of the body. So you can look and see if the body's working right or not. And if it being radioactive, you could measure, if you want to see if, the blood is flowing to all parts of the body, you could check and see if it goes to all parts of the body. A famous one for this is 99 molybdenum MO. That's one of the elements I really can't say. But you can use this here as an idea of finding out where in the body, because that radiation can come out of the body. Not so strong, but then we can see, here all of this element here is going to this part of the body, so maybe there's a problem here or it's not going to another part. Really clever, really good use of the science, and it's all because it's the same element, the same protons, the same electrons therefore, so there's the same reactions that are normal in the body. But the neutrons are different, and that might make it radioactive, and sometimes we can use that radioactivity for good. Thank you.